Hi, welcome back. I want to talk with you this morning about the graph of secant. Now, I want you to remember that secant theta is equal to 1 over cosine theta. So, what we should not be surprised about is that secant will be undefined wherever cosine equals 0. So we're going to see a graph with a lot of vertical asymptotes. And those vertical asymptotes are going to occur where theta equals 0, pi, 2 pi, and so on. And in fact, we can go the other way. So, in other words, whoops, wait, I lied to you. That's not correct. That's not right. Cosine is related to the x-axis, so we're talking about at the verticals, right? So we're talking about pi over 2, 3 pi over 2, and 5 pi over 2, 7 pi over 2. In other words, at pi over 2 plus or minus k pi, where pi is any integer. So I'm going to go ahead and show you the graph of secant. And then we're going to talk about some things. So this is kind of an odd looking graph, and I'm going to explain to you what this is. The red curve in here is just cosine theta, and I put it in for reference. And this really helps anytime you're graphing either secant or cosecant. We'll talk about cosecant in a minute. Because what you do when you graph secant is you really take cosecant and you blow it up. So the black curve is the graph of y equals cosecant theta, which is 1 over theta. So what do we notice? Well, we notice that this has got kind of a no man's land in between here, right? That we've got upwards facing u's and downwards facing u's. And these aren't parabolas, these are u's. We notice we've got some vertical asymptotes here and here and here. And we also notice that this function secant, I'll fix that in a second, secant actually never crosses the x-axis. Okay? Oops. So let's talk about this. So the domain of secant, we can really put any x value in, right? So the domain of secant is all real numbers. The range is a little tricky. Actually, that's not true, is it? Because secant is undefined. So at certain points. So the domain is theta not equal to pi over 2 plus or minus k pi, where k is any integer. Okay, I just did something weird there. I want to tell you what I just did. Let me come down here. I just wrote k is an element of j. So this reads as k is an element of the set of integers. You may or may not have encountered that particular shorthand before, but J means integers. And this little Greek symbol epsilon means is an element of. This is a math way of saying k is any integer. Okay. The range of this function is also a little weird. It is negative infinity to 1 unioned with 1 to infinity, which really says that a plain old unadulterated secant function won't be any smaller than 1. Well, it won't be, you can't find a secant value, an output from the secant function between negative 1 and 1. If you think about what it means to reciprocate a value and the limits on cosine, that will make sense to you. And the period, so we can talk about the period of secant because it repeats. It repeats here and here and here. And you can see the period is 2 pi. We can also talk about a midline. And the way to think about the midline of a secant function is to think about the midline of the cosine function from which this secant would be generated. So in this case, the midline would be the line y equals 0. And we can also talk about not necessarily the amplitude of the secant function, but we can talk about the amplitude of the cosine function from which the secant function is generated. So we can talk about the amplitude. And the amplitude would be this distance from the bottom of the trough to the midline. And that will be 1 for a pure unadulterated secant function. Now cosecant is very similar, which hopefully doesn't surprise you, because cosecant comes from sine, which is very similar to cosine. And in fact, so cosecant, remember, is 1 over sine. And we remember that sine is a horizontal shift of cosine, and in fact, cosecant is also a horizontal shift of secant. So let's take a look at the graph cosecant. And I'm actually going to, let me do this. I'm not done with my secant yet, so I'm going to put this away. Okay, there we go. I'll turn that off. Now let's add another folder. I'm going to put cosecant in there. Okay. And so what I want to graph is, remember, cosecant comes from sine. So I'm going to start with a sine function. And I'm going to make it dash so that we know it's just for reference. And now, and actually I'm going to, let's see what I use. I used capitals. I'm going to make this one that I can adjust later. So I'm going to put in my multipliers and my shifts, because we're going to talk about that in a second. Okay. Now let's put in cosecant, and I'm sure you know what it's going to look like. Oops, let me make it an adjustable one. Okay, and I'm going to go ahead, excuse me, and I'm going to pull this in so we can scribble on it. There it goes. And if you compare the graph of cosecant to the graph of secant, the only real difference is where the vertical asymptotes occur, which will affect the domain, right? So the vertical asymptotes for secant appear where cosine equals 0. The vertical asymptotes for cosecant appear where sine equals 0. So again, for reference, this green curve is the function y equals sine. I just put it on there for reference. The purple curve is y equals cosecant. Okay, so let's talk about the cosecant function. The domain for cosecant is theta cannot equal any k pi, where k is any integer. The range, like cosecant, secant doesn't appear between 1 and -1. It's undefined in those regions. So our range is anything below -1 or anything above 1, inclusive, just like secant. The period of this function is 2 pi, and we can talk about an amplitude. Whoops, sorry. Amplitude of 1, and the midline for an unshifted cosecant will be the x-axis. Okay. Now, I put in those adjusters, and let's take a look at that. Let me pull those out, actually. So I put in our external multiplier and our internal multiplier and our c. These affect secant and cosecant in exactly the same way they affect sine and cosine. So if I make my a be bigger, my cosecant curves, the halves of my cosecant function, get further apart. If I change my internal multiplier, my period changes in the expected way. Right? If I change my external adder, my midline moves up or down. All right. So now you're an expert on the graphs of secant and cosecant. We'll come back in another video and we will practice these skills.